Welcome everybody to our second day of the Australian Algebra Conference. And our first speaker today is Roozbeh Hazrat, who is supposed to be from the University of Western Sydney, but I think he might be in Germany. And Roozbeh is talking about irreducible representations of Leavitt algebras. Take it away.
All right. Yeah, thank you so much for the opportunity. So let me start with a subject that I didn't know about it until 2-3 months ago, and some of you might know about this, but let me just go ahead and tell you just the basic, and then tell you the name of that subject. So I'm going to start with a grid, and imagine you have 4 objects sitting here. It could be 4 chips, or in the theory, they say 4 grains of sand. And as you see, there are here 4 edges going out. So now you're allowed to move these chips along these edges. Okay, so if you do this, what you get is, so you see these chips here moves here to the other nodes. So what you get here is 1, 1, 1, 1. Okay, so I move the chips along these grids. Let me give you one more example. So imagine now you have 4 chips or grains of sand here, and maybe say 2 is sitting here, also 2 is sitting here. Okay, let's do the same game again. Now these 4, one of them goes up, 1 here, 1 here, 1 here. So I get 1. Now here I had 2, so I get 3 now. Here is 3 and here is 1. Now see what happened. Now 1 is sitting here, that's fine. 1 is sitting here, but now there are 3 here and there are 3 edges going out. So if this happens, that there are more grains of sand or equal grain of sand than edges, then so to say this vertex fires again. So this 3, 1 goes up, 1 goes back, and 1 goes here. So I just do that, 1 here, 1 here, 1 here. I already had 1 and 1 here. And the same happens for this one. This vertex fires. So I get 1 here, and 1 goes back, and I get 2 here. Okay, so this is the distribution of these grains of sand along these grids. And now it stabilizes here because there is 1 sitting here, but there are 2 edges going out. So you are not allowed to fire anymore. Here also it stabilizes because there are 2 grains sitting here, but there are 4 edges. So you cannot fire anymore. Okay, so now where does this come from? First of all, there is a terminology for this model. It's called self-organized criticality. So what does this mean? It means that if you have a system like this, and there are these grains of sand or chips or objects sitting here, and there are more than actual number of edges, it's gonna fire. And it keeps doing this without any force from outside. It keeps doing this process until it stabilizes. So self-organized, meaning it keeps doing this without any output from outside, and organized here stably, but barely stable. So criticality means it's barely stable. What does that mean? That means if I add 1 grain of sand here, it becomes 2 and it fires again, right? Or if I add another grain of sand here, it becomes unstable and fires again. So it's stable, but it's barely stable. All right, and then this was introduced in 80s by Bach, Tang, and Wiesenfeld, and this idea came from physics. But then Bach wrote another book called, this book has not much mathematics, it's just philosophical. It says How Nature Works. And he basically argues, look, a lot of things has this sort of behavior, maybe traffic jams. So if there are cars here and there are 4 roads, then cars are going to go around this, these grids and, until it's stable. Or forest fires. So if one tree gets catch fire, then it's going to distribute this way to the next trees, and it continues until the whole forest gets fired and I don't know, stabilizes. So this is a cute book, not much maths, but it's sort of even stock markets, it behaves like this. So he argues like that. Okay, so now just to show you that there is actually something in this theory, let me change this to a very, very large grid. Okay. And now imagine here, this is in the middle, sits 1 million grains of sand. Well, as before, so there are 4 of them moving up here. So it gonna fires, there are in 1 million, so it keeps firing, and it's gonna distribute. And what do you think I would get here? What kind of arrangement you think I would get here? And let's see if you can guess that in your head. And just look at this. So it was here just 4 grains of sand and it distributed. Imagine I have 1 million of them. What would happen? While you're thinking, I'll show you the picture. And that shows there is something in this theory. Here it is. No, not that one. This is the distribution of 1 million grain of sand. And the way it's done here now is that 1 million grains of sand sitting here, and I distribute, and in each vertex is sitting either 0 or 1 or 2 or 3 grains of sand. So I assign some color to that. If it's 0, maybe I just put black. If there are 2 grains of sand, I do blue, 3 green, and so on. So you got the idea, and you get this sort of this fractal. And if you look at the literature, it says, we don't understand why you get such a nice fractal out of this distribution of sands. Okay, now the name of this theory, I guess some of you might know, but I didn't. It's called sand pile model. Sand pile model. And there are a couple of theorems you can prove. One is that if I put here 10 grains of sand, in here 5, and here 3, and start firing, one of the things you can prove is that it doesn't matter if you start firing from this node first and then do the firing from this node, or the other way around. If you start from here first and then from here. It's not immediate to me why they have the same effect, but you always get the same thing. So it doesn't matter which node fires first. Therefore, it's called abelian sand pile model. The other thing, and this is a bit more difficult to prove, is that you can prove it stabilizes, as you see. If I have 1 million grain of sand here, it stabilizes, but it always gets you a unique form. So it doesn't matter which one fires, which matters the way you are basically reducing things, you always end up with the same shape. So it's uniquely stabilized. And you have to prove that, but it happens. All right, let me change this a little bit. Now, imagine now this time I'm looking at the grid as before, but this time I'm gonna go look at the directed graphs. So that means you know in which direction the sands are going. So this is a directed graph. This is the direction of this edge. So if the sands are gonna go somewhere, it's gonna go in this direction. It's not gonna go in the other direction, as you see, okay? So it's gonna go in this direction. And the other thing I put in this model, I have one node here, let me call it sink, that if the sands get here, it vanish, right? I mean, if I'm talking about, I don't know, your money, if you get here, you are gonna lose your money. Or if the grains of sand comes here, it gets off the board. So it's gonna vanish. So this is the theory. So let me just give you one example here. Imagine I put 3 chips here, 0 here. This is U, this is V. So you are in 3U. And now if this 3 fires, 1 goes here. Okay. Now 1 goes back here and 1 already here. So I get 2U plus V. Now, another time, I have 1 here, 1 here. There are 2. So 1 goes again here, 1 goes back. So I get 1U plus 2V. So let me just put 1 more here. So I start with 4. So 3, 2. So this fires again. So I get 1U plus 3V. So at this moment, I have 1 here and 3. Now I can use this V because 3 edges getting out. So it fires. 2 of them disappear and 1 goes back. So I get 2U, and then again this fire. So you got the idea. I get 1U plus 1V, I guess. So this is the stabilized form. As you see, I need to do a bit of work to get that. Okay, so this was introduced, just this process, and came 10 years later, somebody called Dar, and he assigned some monoid and therefore some group to these sand pile models. And the way he did that is, imagine now these are your vertices and these are the sands sitting there. If you have one bunch of these and if you want to add another one, okay. So these are vertices, let me call it I, and these are the sands associated to that. What you do, first of all, you can stabilize this because we have a theorem that you can always stabilize. Well, just follow your nose, add these two, and then stabilize. That gives you a monoid. So you have to prove this is a monoid, but it gives you a monoid. Now let me call it a sand pile monoid of E. And this is an abelian monoid. Then I can do the group completion of this. So group completion, always from a monoid, you get a group. So Dar introduced this monoid and this group, and he showed that some of the properties of that sand pile actually reflected into this group. For example, you can ask, okay, what happens if in this monoid you have an idempotent? What does that mean in that sand pile model? Or maybe this monoid is conical, meaning if A plus B is 0, then genuinely A equal to B is 0. If your sand pile is conical, what does that really mean in that sand pile model? Okay, I'm gonna leave this here. I have another 5 minutes, I think. In a very different direction, there is a subject called Leavitt path algebra. Has nothing to do with this. You start with the graph E, and this is a directed graph. And you assign to this graph an algebra. And in a second, I'll tell you the relations between these. I have to be very quick, but the relations is such that it behaves very nicely. Namely, the algebra gets very nice properties. And oftentimes, you can give it if and only if theorems between the properties of this algebra and properties of this graph E. For example, you put here when this algebra is simple, and you can characterize this graph E. When this algebra is, I don't know, Noetherian, and you can characterize this E. There are like 50, 60 papers, you just put your favorite adjective for the algebra, and oftentimes you can get if and only for the graph. So, and I want to go in one go and define something called the weighted Leavitt path algebra. So imagine each edge has a weight here. So I just show you the relationship here. I know I don't have enough time. So if each edge comes with a weight, here is the relations you put here. First of all, the algebra is free algebra on all the vertices, edges, and ghost edges. These are the edges going backwards. So I add edges going backwards. So you have a chance to go backward also. And the relationship, I just want you to get just a feeling. It looks like this. First of all, you go along this E1 because edge is E with 3, with the weight 3. So I call it E1, E2, and 3. And you go with the ghost edge back. You do the same with F, and you do the same with G, and then you retrieve the U. So this is the idea. So you are standing here, you walk along all these edges, and you come back, and you get U, and you imitate that for all of them. Okay, and this is the algebra, more or less. And the first thing you often want to study in algebra is its K-theory. So what is the K-theory? So if you start with the ring A, so imagine it has an identity, get all the projective modules and get all the P-projective modules finitely generated, and get the isomorphism classes of all those projective modules. That gives you a set. Let me call it V of A. And you can add these projective modules. If you have two projective modules, you can add them. And that gives you also a monoid. Therefore, you can complete this and you get what we call a grotendic group, so another group. Okay, so now I have 2 minutes, I think. Here is the punchline, and I don't understand why this happens. So let me just write down the theorem. And this theorem by Gene Abrams. Gene is in University of Colorado, and it was really his observation, but I happened just to hang around there, is that if E is one of those sandpile graphs. So remember, you have a directed graph and there is a sink at the end that, you know, the vertices, the chips are gonna disappear. And you had this sandpile monoid. It just happens to be the monoid of this algebra. So you can look at this E as a weighted graph. You can associate this Leavitt path algebra and get this monoid comes out of projective modules. And this is really, I don't understand why projective modules of some ring happens to be this firing of these ones. But this happens to be the same. Therefore, the DARS group, this sandpile group, is the grotendic or the K group of this algebra. So that opens a lot of doors. First of all, what are the properties of these sandpile models that you have? So you have all kinds of properties of this sandpile. Can you see this as a structure of this algebra? Because there's a tight relationship between them. In fact, this is what we call now a sandpile algebra. Because you can show in the theory that there is a universal way to construct an algebra associated to this monoid, and that universality is happening here. So you have now an algebra associated to these sandpile models, and the question is, okay, so now, for example, that fractal I showed you, if you assign the Leavitt path algebra to that grid, what does that mean there? What kind of properties of the algebra you would get? All right, I think I need to stop here. Thank you.